that feel right? Great. Is everybody with me? Okay, so when we talk x bars, this is what we would use if we're doing a quantitative variable. Now, let's go ahead and take this through a little bit further. Okay, so could we go through and I could get a number from every single one of you? All right, could I make a graph of each of those numbers? All right, so I'm going to call this my sample data. There's 8 of you, and we could have a dot plot for each of you, a dot for each of you on our dot plot, something like that, yeah? All right, how many samples is that? Sure, I'm right there. That is 1 sample. Is everybody with me? Okay, so the reason I'm pointing this out is we've got a sample, we have a sample mean, we have a distribution of a sample mean, and out there there's like 3 different means that we have to think through in this particular case, okay? All right, so we have the mean. This is the true mean of the population. So that would be the mean of all the students in Grandview. Is everybody with me so far? Okay. We have x bar. Is everybody with me? So in this case, x bar would be the mean of this 1 sample. Is everybody good? Okay. Lastly, now let's imagine each of us goes out, takes a sample of students, right? And if we each go out and take a different sample of students and ask them how much they spent for lunch, we're all going to get a different sample mean, yes? That's what this picture is, right? We each get a different sample with a different mean. Okay? And so we have one more type of mean. The center of this one is the mean of the x bars. So mu of x bar is the mean of the sample means. Okay, now, some things I want to point out. Well, hold on. All right, so just like when we were doing the p-hats, there are rules for when this distribution of possible samples will be normal. They have different rules for the mean and different rules for the standard deviation, okay? All right, so those sample means will be normal under one of 2 different circumstances, okay? The first of which is I'm sampling from a normal population. If I know that the population I am sampling from is approximately normal, then I know that all those sample means are going to be approximately normal, okay? If I don't know anything about my population, what I need to know is that my sample will be large enough that it's representative of the population so that the means will be about the same each time. Is everybody okay? And that happens when our sample size is large enough, which means our sample size has to be greater than or equal to 30. So no matter what about the population, if our sample size is bigger than 30, we can assume that if all of us took a different mean, that those means would still be like pretty darn close to each other. So do you guys remember the other day we had that program online up where we like took a sample and I said, watch the sample, right? The sample, like when we pulled from a super skewed distribution, every single one of those samples was skewed to the right, but the means were all about the same. So because the means were all about the same, the graph of just the means themselves was approximately normal. Is Everybody okay? All right. So, speaking of the means, what that means is that the mean of the sample means will always equal the mean of the population, because the mean is unbiased. Everybody good? The standard deviation of the sample means is the standard deviation of the population divided by the square root of the sample size. By the way, these two are on your formula sheet, yeah? Okay, so you don't need to have these memorized. It's more important that you can make the distinction of, here's a context, I need to decide, is this something where I need to be using these formulas, or is it something where I need to be using the p-hat formulas? Okay, so we'll have some time to practice that. All right. Okay. The height of a young woman follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5 inches. You guys, what type of variable do we have if we are talking about height? Quantitative or categorical? Quantitative. The fact that this is quantitative is what's going to make me start thinking, okay, I'm dealing with means. Is everybody okay? And this is going to feel pedantic at first when I continually go after that concepts, but I promise you I'm laying the groundwork for where you're going to get confused in a couple weeks. Okay? All right. So if I'm randomly selecting a single young woman, heights are normal, the standard deviation, the mean is 64.5, the standard deviation is 2.5. What is the probability that a woman is 66 inches or taller? How are we feeling about this picture? And we're just finding the probability that an individual observation is more than 66. This should feel pretty reviewish for you, yeah? Where do I find this answer? What do I use in my calculator? I'm sorry? Inverse norm is going to ask me for an area. I don't know. I'm trying to find the area. Normal CDF is going to ask me for boundaries. Do I know the boundaries? Everybody good? Okay. How are we feeling so far? Would you say that it is likely to get somebody who is 66 inches or taller? I wouldn't call it unlikely. I would put it in the it could happen range, yeah? Are we good? All right, so now, let's say I take a sample of 10 young women and find the average height. Would we expect the average height to be 66 inches? Let's think through. Why not? You just said it's reasonably likely to get somebody who's 66 inches tall. What would it take in order for the average height of my sample to be 66 inches? That would mean 10 people, right? Imagine I had to pick 10 dots off of this graph, right? Whose average was right here. Most of my dots would have to be over to the right of it, right? Most of my sample would have to be bigger than 66, or would have to be above average, yeah? In order for that to happen. In fact, you probably couldn't even have a shorty pants like me in that sample because I would pull the average way too far down. Yeah? You guys, are we catching this? All right. So how does my picture change if my sample size is 10? So one of the things that it might be worth noting is if I had to put this into symbols, right, this first statement, I am finding the probability that my sample mean is greater than 66. Is everybody okay? And man. So then I might want to start thinking through what would the distribution of possible sample means look like. Like I take a sample, there's its mean, and then Leva takes a sample and this is that mean, and then Andrew does, and then Carter does, and then Ben does. Are you guys all with me so far? Okay. Now, we won't all have the same mean, right? We all agree that our samples are all going to be different because samples are not perfect, right? Okay, but can we agree that on average, they're going to be about how big? Yeah, they're going to resemble the population mean. They're just not going to be perfect. Is everybody good? And then they certainly are going to be less spread out than individuals, yeah? So how less spread out? This is where we can use that formula for the standard deviation of the sample means. Okay? And so we would use 2.5 divided by the square root of 10. No, you didn't. 0.79? 0.079? Oh, wait. For the standard deviation. Got it. Okay. No, I got it. You guys, I thought you did the probability already, and I was like, there's no way that's the probability. Now, you guys, if my standard deviation is 0.79 instead of 0.25, 66 is much further away when this is my standard deviation than it is here. Everybody good? I don't know what the answer is. What is the probability that my x bar will be greater than 66? So, again, if that's the case, we want to use the mean of the x bars and the standard deviation of the x bars within our normal CDF. Because we're not finding the probability of an individual, we're finding the probability of a sample mean. That's great. I needed it to be lower than this, and so when you guys said the 0.79, I thought you were answering this question, not this one. All right, everybody good? Lovely. I'd like to have a small conversation before we turn the page about vocabulary. You guys, answer the following question for me. Why would it be advantageous to instead ask a group of 20 young women instead of 10? Why do we want to have a larger sample size? Less variability in what? The less variability, when you say the mean, we just said we have 3 different types of means. Do you guys see? Are you guys starting to feel my gist here? Okay. So communication in this case becomes incredibly important. There is less variability in the distribution of the sample means. You guys see what I'm saying? There is no variability in the population mean, and for any one given sample, there is no variation in that sample's mean. It's variability in where that sample fits compared to other possible samples. Do you guys see what I'm saying? There's another mistake that kids make all the time when they talk about increased sample size, and they say by having 20 samples, you have less variability in the mean. You guys, if I go from asking 10 people to asking 20 people, if I ask those 20 people, how many samples am I taking? 1. What I have done is increase the size of that one sample. Do you guys see that subtle difference? Okay, you're not going to 20 samples. You're going to one sample still. It just so happens that there's 20 observations within that one sample. And I just want you guys to kind of think through some of that language. You want to be really, really careful. Okay? And you're no longer really, you should not say the mean. You should say the sample mean, or the population mean, or the mean of the possible sample means. Okay? So when we say there will be less variability with that larger sample size, there'll be less variability in the possible sample means, in the distribution of sample means. And you guys see the subtle difference, but it's actually a really, really important one. Okay? So you're going to see me, I'm telling you this, you're going to see me be very picky when you use the word mean from here on out. Okay? If you just say the mean, I will interrupt you right mid-sentence and say, what? What kind of mean? Because I want us to start thinking through. I want you to hear my voice inside your head saying, what kind of mean? So that when you're taking the test and you're writing down the sample mean or the mean, you should hear me. The what mean? Everybody good? Oh, I should make one. I have more buttons to make. Okay. We're going to do the top example and then we'll take a break, okay? I'll let you read it. I've worked this example thousands of times. It's a good example. Okay, so far, basic premise is a company would care about how long it takes somebody to do something so that they know how to schedule them, yeah? So as you look at this graph, like the big idea of this graph is most of the time, this is an easy fix for the guy, yeah? And every once in a while, it's not. Cool? All right, what is the probability it takes an individual guy more than 1 hour, or more than 1.1 hours? Anyone? Why can't I just do an individual right now? It's not normal, right? Like, I don't know, this is the graph of individuals. I don't know how to do that. Everybody okay? I got great news. They're not interested in one guy and any one individual thing. Like, when you think about they're trying to schedule out their technicians, they're hoping to have more than one. You guys see what I'm saying there? Okay? Because if you only have one fix, that's not a lot of money, right? They don't care about the one individual. They want to think about big picture what's going to happen if they have a lot of appointments. Will they leave themselves enough time? Is everybody good? Okay, so in the coming week, the company has to do a simple random sample of 75 air conditioning units. Okay, already we know what? N equals 75. And knowing that n is equal to 75, we can say, well, 75 is in fact greater than or equal to 30, so the x bars are approximately normal. So even though the population isn't, the means will be. Everybody good? All right. We know the mean of our population is 1.1. So the question really becomes, is this enough time? So look, let's go ahead and look at what is the probability Wait. We know the mean is 1. Yeah. So if the means are approximately normal, on average, it's going to take them 1 hour to do the job, right? What's the standard deviation of the time it takes them to do the job? Nope. What is the standard deviation of the mean amount of time it takes them to do these 75 jobs? It would be 1 divided by the square root of 75. Okay, so because we're looking at the average time it takes them, we're going to use the mean or the standard deviation of, the averages. Cool. All right, so now, what is if they budget 1.1 hours per machine, so they're budgeting a little bit more than average, what's the probability they'll need to pay overtime? That's essentially what the question becomes, yeah? What is the probability it's going to take, on average, more than that 1.1? Which is, what is the probability the mean is bigger than 1.1 hours? Okay, so there's about a 20% chance that they didn't budget enough time. It sounds close. Your lower would be 1.1, your upper would be a gajillion. Your mean would be 1. You are using normal CDF.
I got like 2.0. Sorry, 0.2. That's what I got. I got just 0.18.
Okay, so what's really happening? How many of you, did we all use exactly 0.12 as our standard deviation, or did we use different rounded versions of the 0.12? You use 0.12?
Without writing, it's 0.115.
115?
Yeah, that's what's nice. But for the standard deviation.
Oh, got it. Okay. So yeah, if you rounded the standard deviation different, you're gonna get a different answer. It's fine. Okay. They'll be close, right? We're all roughly 20% because everybody good? Okay. All right, let's take a break.